Okay, this is a series of videos on probability. Let's start with the basics of probability. Okay, for this you need to know certain things called, say, sample space. The notation for sample space, sometimes it's U or sometimes it's like this. Okay, and you also need to know what is meant by event. So usually events are denoted with capital letters A, B, etc. Okay, so what is sample space? Sample space is when the experiment is done and the sample space contains the outcomes of the experiment. For example, the experiment is rolling a die. Okay, the action that you are doing is the experiment, and the outcome is the set of numbers 1, 2, 3, 4, 5, 6. So this is the sample space. Okay, event is a part of the experiment that is done. Say for example, uh, event is getting 4 while rolling a die. Okay, so this is an event. Say A is equal to getting a 4. Okay, so your A would be the set just 4. Okay, so this is what you need to know before you go into actual probabilities. Okay, now what is probability of A mean? A probability of A is probability of getting a 4 when a die is rolled. Okay, the formula, the definition for this is the number of elements in set A divided by the number of elements in set U. Okay, here it is 1 over 6. Okay, so you need to, this is a very basic definition of a probability: n of A union n of A divided by n of U. Okay, so what you have to do is you should know how many elements are there in U and how many elements are there in A, and you just need to divide them. Okay, there are certain properties of this probability. Any probability of an event, and a probability of any event cannot exceed this range. That is, it can be only between 0 and 1. Okay, what is it if it is 0? That means P of A is 0, right? This implies that the event A never occurs. Okay, it can never occur. And what if the event has a probability of 1? It's very certain that the event occurs. Yeah, 100% sure. That is, say for example, in the same question of rolling a die, if you define the event A as getting, not a set, getting a number between 1 and 6. Okay, so this A would be all the numbers 1, 2, 3, 4, 5, 6, and n of A would be 6, and n of U, as we have done, is 6. Therefore 6 over 6 is 1, which is the probability of this event. So it is a sure um, idea that you will be getting a number between 1 and 6 when you roll a die. So when you get probability of an event to be equal to 1, then that event is very much certain to occur. Okay, 100% sure that it occurs. Okay, any other event would have a probability between 0 and 1. Okay, that is one property. The other property is, as we just said, when will it be 0? P of A would be 0 when the A never occurs. Or you can also talk it like, put it like P of phi is equal to 0. Phi means null set. Okay, and probability of the whole set, that the sample space is always equal to 1, because probability of U would be n of U over n of U by the definition, so it is 1. Okay, so these are the two things, very important things. Probability of null set is equal to 0, and probability of the sample space is always equal to 1. And we talked something about mutually exclusive events. Okay, what do they mean? Mutually exclusive, two events, you need two events, A and B. They are called mutually exclusive if probability of A union B is probability of A plus probability of B. That is, A union always represents the word or, and intersection represents the word and. So A union B means either A or B. Okay, so that means either A occurs or B occurs, and if they are mutually exclusive, then it is equal to probability of A plus probability of B. Okay, so we'll come back to this using Venn diagram soon. Okay, in other words, if they are not mutually exclusive, then it will be P of A plus P of B minus P of A intersection B. So it is very obvious that for mutually exclusive events, P of A intersection B is equal to 0, because you don't have that here. Okay, so from this, if you go to this equation, then it is obvious that this part is missing for mutually exclusive event, which says that P of A intersection B is equal to 0. Okay, let me represent these in Venn diagrams. Generally, if you want to say what is probability of A, this means the event A is a subset of the sample space. Okay, so you'll know that P of A is number of elements of A divided by number of elements of U. Therefore, A has to be a subset of U. In other words, when you have two events, that is, you can have two events, for example, rolling a die and tossing a coin, or you can have rolling a die and rolling a die two times. There are so many possibilities of having two events. Two events can be in two different forms, either they are like this or they are separate. Okay, so in this case you have A intersection B, it is there, right? It is not equal to, probability is not equal to 0. In this case there is no A intersection B, therefore probability of this equal to 0. So you would have guessed now that this is the condition that is satisfied by this diagram. Therefore this diagram represents mutually exclusive events. So what you can see here by this diagram is for mutually exclusive event A union B, number of elements of A union B is number of elements of A plus number of elements of B, right? Whereas in this case, n of A union B would be n of A plus n of B minus n of A intersection B, right? Because you are adding it twice. You know about how to find this. Now if I divide both sides by n of U, that's how we are getting that formula. So in the left hand side of each of these equations you have probability of P of A union B, and this is also probability of A union B, because n of A union B divided by n of U. And on this side you have P of A, n of A over n of U, plus n of B over n of U is P of B, and there is a minus P n of A intersection B divided by n of U is P of A intersection B. So this is the formula I just wrote a few minutes before. And here you can see this is P of A and the other one is P of B. This is for mutually exclusive events, and just a few seconds back I wrote this formula. Okay. Now there are three ways of representing the events and the outcomes. One is just we did Venn diagram. The second one is tree diagram, and the third one is lattice method. Okay, lattice table. So let me start with lattice and give you an example. For lattice you can have an example like rolling two dice. Okay, if you have rolling two dice problems, then you can see that you can actually put them in lattice diagram form. That is, you should be doing something like this, a grid type of diagram. So this would be 1 2 3 4 5 6, because when you roll a die you get these numbers. Okay, and how do you represent them? So you can have, this is the first die and this is the second die. So when you roll two dice like this, then you can have 1 1 2 1 3 1 4 1 5 1 6 1, and you can just fill the whole thing like this. This is known as lattice diagram method. Okay, so if you fill this, you know that there are going to be 36 crosses on over the board. Okay, if you want to find probability of getting a 1, right? Then how many ones are there? You can have 1 1 1 2 1 3 3 1 sorry, 1 1 2 1 3 1 4 1 5 1 6 1, or 1 2 1 3 1 4 1 5 and 1 6. So there are 1 2 3 4 5 6 7 8 9 10 11. So getting 1 is 11 out of the total of 36 stars. So the probability of getting 1 is 11 over 36 using lattice diagram. Okay. Tree diagram would be like, you have two events like tossing a coin or tossing a coin twice. Okay, so the outcomes are head or tail. Okay, so in tree diagram what you are supposed to do is you should have the branches for every event. So there are a coin twice, right? So it is like you have one event. This is the first time that you are tossing the coin, and this is the second time you are tossing that coin. You don't need to draw this. Okay, what will be the outcome of the first event? The first event has two outcomes, head or tail. Okay, the second event can have two outcomes each, head or tail, head or tail. So this is how you are supposed to draw the tree diagram. If I have thrice, then I will have one more event coming up, and for each I'll be having a branch, two branches. Okay, so the vertical groups gives you the number of events, and the horizontal branches give you the outcomes of each event. Okay, it could be anything. It need not be tossing a coin thrice. It could be tossing a coin and rolling a die. So if it is tossing a coin and rolling a die, then you will have the first event to be tossing a coin. Okay, and the second would be rolling a die. Okay, so tossing a coin has two branches. Rolling a die should have six branches, right? Because it is 1 2 3 4 5 6, so it should have six branches. So for each branch of tossing a coin you should have six branches coming out. Okay, so this is how you do your tree diagram. So these are the three methods of drawing diagrams for any probability question. Let's do some example. Okay, this is a question. A bag contains 20 coins numbered 1 to 20. A coin is drawn at random and its number is noted. What is the probability that the coin has a number that is divisible by 3 or by 5? Okay, so by the moment you see or, you know that it is a union problem. Okay, by 3, let me take the numbers that are divisible by 3 as t, and the numbers that are divisible by 5 as f. Okay, so what are the numbers between 1 and 20 that are divisible by 3? That's what you are supposed to do first. 3, 9, 12, 15, right? 18. You have 18 as well before 20. Okay, divisible by 5, it starts with 5, 10, 15, and 20 is also included. Okay, so you need to find T union F, right? Probability of a number that is the number is divisible by 3 or by 5, so T or 5. Okay, so this is n of a T union F divided by n of the total sample space. Okay. Or you can directly use the formula, which is P of t is 1 2 3 4 5 5, and the total n of u is 20 because there are 20 numbers. Okay, so 5 over 20, f you have 4 over 20, and t intersection f is you have common numbers are 15, right? It's only 15, so it is 1 over 20. So if you do this, I think we have left a number here, 3 6. Okay, so this is 6 over 20, 4 over 20, and so much. Intersection is only one number, 15, therefore 1 over 20, which would give me 9 over 20. Actually you can do this directly as well. So T union F would be, you can just find what is T union F, which is 3 5 6 9 10 12 15 18 and 20. right? And if you count them, there are 9 numbers, so 9 out of the total 20, and you get the same answer. Either you can use the formula like this, or you can directly use this formula. Okay, so when do you use Venn diagram? You can see that the actual Venn diagram was not necessary here, though you used the concept of sets, right? You didn't actually draw any Venn diagram. But which type of questions do you have to draw Venn diagrams? Let's look at an example. Okay, for this you surely need a Venn diagram. It's obvious that P of A intersection B is not equal to 0, therefore the diagram should look like this, right? This is A, there should be an intersection there. Okay, what is B complement? B complement would be this part. I think you are thorough with set theory, so you should be able to draw what is A intersection B complement. So A intersection B complement would be, this is A, so where you have both the colors, right? This is the part which is A intersection B complement. This is A, this is B, and you can see that this can also be written as A minus A intersection B, right? You are taking away the A intersection B from the A. Therefore, I can rewrite P of A intersection B complement as P of A minus P of A intersection B. And you can see that you can just substitute the values. P of A is 0.6 and P of A intersection B is 0.2 and the value is 0.4. Okay, so you can understand that you need the diagrams, drawing diagrams for such questions. Okay, let me do one question for tree diagram. Example. Okay, this is the question. So tossing a coin 3 times. It's always better to use tree diagram for such questions. Okay, so you have 3 vertical sections here. So as I told you before, there are 3 events happening. So the first event would give you 2 options, H and T, and the second event has 2 options for each of the first branch, and there are more branches for the third event, that is tossing the third time. Now you need to find the probabilities. You need to write them on the branches. So what is the probability of getting a head out of by tossing a coin? It's obvious, it is half for each, so it's going to be half everywhere. Now you need to get 3 heads, so getting 3 heads comes along this way, this one, this one, and this one, and that is the only way that you can get 3 heads, H, H, and H. So what you need to do is just multiply the probabilities there, half times half times half, which is 1 over 8. So getting 3 heads is 1 over 8. Getting at least 1 head, which means you can see that it's underlined, at least is 1 head, 2 head, or 3 head. Okay, except getting all the 3 tails. Okay, which means that you need to avoid this particular path except this, right? So except this, you need to get all the other combinations. Okay, so what is the probability of this? T T T, which is half half half, which is 1/8 again. So you are going to collect all these probabilities except this, right? Except 1 over 8. We know that the total probability is always equal to 1. So what you want to do is you need to just subtract 1 minus 1 over 8 to get the rest of the probability here. So it's 7 over 8. So here you can see that the tree diagram is very helpful. You could have even gone by using this individually, that is, you could have got this is H, H, and T, and this is H, T, H, and the next one is HTT, and so on. You could have done this, and you could have found the individual probability, and you should have added them. Okay, this is another way of doing it, except this you are not supposed to do. So you can find all these probabilities and add them here, then you will surely be getting 7 over 8. Okay, you can try this out if you are not very confident about this. Okay, we'll do something called conditional probability. Here we do not consider the whole sample space but a part of it. Okay, so we are not going to consider the U as it is, but we are going to consider a part of U, say something, another set which is a subset of U. Okay, so you're going to consider, if you have a U and you're going to consider this as your U, and then you are going to give an event which is inside this A event, and then you are going to see what is the probability of this event occurring inside this event. Okay, that is known as conditional probability. So what is probability of B given A? Okay, that is known as conditional probability, that the event B depends on the event A. So there is a condition on the event B being occurring. Okay, for example, let's consider rolling a die. When you're rolling a die, you know that you're going to concentrate on the outcomes greater than 4. Okay, so rolling a die is universal set gives you 1 2 3 4 5, but I'm not going to consider the probability of getting a 5 from rolling a die, but I'm going to consider the probability of getting a 5 when the outcome is greater than 4, which means I'm going to use a new set which is part of the universal set, which is sample space. I'm going to get a part of the sample space, and in this case it is 5 and 6, which is greater than 4, right? And from this part I'm going to get find the probability of getting a 5. So getting a 5 is a single set 5, and I'm not going to consider the probability of getting a 5 from the whole sample space, but from this sample space. Okay, which means that my probability of getting a 5 is 1 over 2. So probability of getting a 5 is 5. So this is probability of 5 from 5 6. Very common use of conditional probability is picking up some colored balls from a box. Okay, there are two conditions in picking up some colored balls from a box. You can pick one ball in the first event, and then you can either replace it and pick the second one, or you need not replace it before picking the second ball. Okay, these are the two conditions. Okay, what happens when you replace a ball? Say for example, I have two boxes of, say, two green balls here and three blue balls. Okay, so if I pick a green ball out of this and if I replace it back, you can see that there is not going to be any change in the total. But if I pick it up and I don't replace it, so this goes off, and then I'm left out with one um, green ball and three blue balls. Okay, so the number changes actually. So this is the condition for replacing and not replacing questions. Okay, and in this case the conditional probability works really well. Let's consider this same example: green balls and three blue balls. Okay, now I want to find the probability of getting two blue balls. When you are choosing two balls at random from this box, what is the probability of getting two blue balls? Okay, the first condition is if you replace them, if the ball is replaced after the first draw. The second condition is when it is not replaced, obviously. Okay, so what happens if it is replaced? So again, a tree diagram would be very helpful here. So you are drawing the ball to ice. So in first draw, you can either have a green ball or a blue ball, right? In the second draw, again, you can either have two choices. I mean, you can have two choices of a blue ball or a green ball. Okay, now to write the probabilities in each branch. What is the probability of getting a green ball in the first draw? In the first draw, you are having, I said you are having two green balls and 3, this is the condition, this is the box which contains 2 green ball and 3 blue balls. So in the beginning you are having 2 green balls out of 5 total balls, so 2 out of 5, and you are having 3 over 5 as probability of getting a blue ball. In the second condition for A, when you are replacing it, it's not going to change, therefore still the green ball, there are 2 of them and the total is still 5, so the probability remains the same. Whereas in this case, if you are not replacing them and you have the same branches for 2 events, the green balls and the blue balls would be the outcomes. Now to write the probability. The probability here would be 2 over 5, 3 over 5, the first draw. For the second draw, when you are not replacing, now in this case you have taken the green ball out, which means you have reduced the number of green balls in the box which contains green. So you have only one green ball and you have only 4 total balls. So this is gone. 1, 2, 3, 4 balls. And you have 3 blue balls out of 4 total balls. And when your first draw gave a blue ball, then this blue ball would have come out, and then but you have 2 green balls here. Okay, so 2 green balls out of 4 total balls, and again you have 2 blue balls out of 4 total balls. So this is how the tree diagram would look like. So what is it when you are getting 2 blue balls? So in the first case, your probability would be along this path, right, which would be 3 over 5 times 3 over 5. Okay, just multiply the branches, and in this case your again the probability would be along this branch, and but the probability would change to 3 over 5 times 2 over 4. Mostly for problems like this, I would prefer you use the tree diagram or the Venn diagram, diagrammatic representation. So the formula for conditional probability, this is A given B, is P of A intersection B divided by P of B, and obviously P of B should not be equal to 0, that is B should not be a null set. Okay, sorry, P of B should not be equal to 0. From this formula, the more useful interpretation of this formula would be this one: P of A intersection B is P of A given B times P of B. Okay, and this type of formula is more often used than the first one. Okay, but there are cases where you would be using the formulas, that is, as we have done already, when P of A, P of B and P of A union B or intersection B, anything is given in numbers. So what happens here is, if you are asked to find P of A given B, then you can use the formula of P of A intersection B divided by P of B. And in order to find P of A intersection B, you can just use this formula. How to find P of A prime given B? So the formula would give you, this is where you actually use the formulas. Okay, so this we know that P of this is P of B minus P of A intersection B. Okay, you can use the Venn diagram as we did before, then you can find it out. Now you can do whatever you have. You have this, you have this, and you have this. You can just substitute the values and get the final answer. Okay, so this is the place where you will be using the formula more than the questions with numbers. For conditional probability, you know there is a condition, that is one is depending on the other. Therefore, there should be the other way where two events are independent. So we have independent events. So if A and B are independent, then P of A given B would be equal to P of A, and P of B given A would be P of B, because the P of B doesn't depend on A. Therefore, there is nothing to do with whatever A gives as outcome. It's just P of B, right? The same with A. It's just P of A, whatever happens to B. Okay, combining together, again, the most commonly used formula for independent events is P of A intersection B is equal to P of A times P of B. Okay. So we'll now look into some properties of these independent events. The first thing is, never assume that two events are independent unless you are absolutely certain that they are. That is, unless you know that P of A intersection B is equal to P of A times P of B. Unless you prove this mathematically, do not assume that they are independent. Okay. You don't have to worry about two, but here the thing is mutually exclusive events and independent events. Mutually exclusive events have P of A intersection B to be equal to 0, while independent events have P of A intersection B to be equal to P of A times P of B. So because for mutually exclusive events, A intersection B is a null set. Okay, therefore P of A intersection B would be 0 for mutually exclusive event. But for independent events, this is the formula. Okay, and you can also have independency on more than one set ABC, and you can see the formula there. What you have to do, how do you show that two events A and B are independent? You find P of A, find P of B, and multiply and see P of A times B, and then find separately P of A intersection B and see that they are equal. So if you see them they are equal, then they are independent.